Hello students, once again welcome to my YouTube channel Physics with Dr. Sanjay Bhargava. In this course of microwave electronics, we are still continuing with the understanding of attenuation. In this video, we'll understand conductor attenuation in cylindrical waveguide, analysis of TM and TE modes for determination of attenuation constant, and then we'll discuss about the Q factor, that is the quality factor of a waveguide. So here we pick up conductor attenuation in cylindrical waveguide. For first we'll do the analysis for TMN modes. Now we must first understand how do we calculate the power lost. So power lost per unit length of the guide is given by PL is equal to RS by 2 HT ka square ds. This integration is over the entire conducting surface. This small t represents the tangential component of the field, is equal to RS by 2 integral 0 to 2 pi H rho ka square plus H phi ka square at rho is equal to A d phi. The TMN modes for circular waveguide are given as. These modes have already been calculated in our earlier videos of cylindrical waveguide. Ez is equal to an jn rho h cos n phi e power minus gamma z. H rho is equal to minus j omega epsilon upon rho h ka square an n jn rho h sin n phi e power minus gamma z. H phi is minus j omega epsilon upon h an jn dash h rho cos n phi e power minus gamma z. E rho is equal to minus gamma upon h an jn dash h rho cos n phi e power minus gamma z. E phi is equal to gamma upon h square rho an into n jn rho h sin n phi e power minus gamma z. Now we need to calculate the power lost per unit length. So power lost per unit length RS by 2 0 se 2 pi omega square rho square an ka square n square jn square h rho sin square n phi upon rho square h power 4 plus omega square epsilon square an square jn dash ka square rho h cos square n phi upon h square a d phi. Now from the boundary condition jn h rho is equal to 0, so the first term vanishes. So this first term becomes equal to 0. Now from here RS by 2 is here, omega square epsilon square an, so we write it here, a jn dash ka square a rho 0 se 2 pi cos square n phi d phi. So this integration would give me limit upon 2, so 2 pi upon 2, that will give me pi. So here we have that pi. So power lost per unit length RS by 2 omega square epsilon square an square a jn dash ka square ah upon h square pi. Finally can be written as RS by 2 pi omega square epsilon square an square a jn dash ka square ah upon omega c ka square mu epsilon. Why? Because h square is equal to omega c ka square mu epsilon. So power lost can be written as PL would be equal to RS by 2 lambda c by lambda ka square epsilon upon mu an ka square a pi jn dash square a h. So this is represented by equation number 1. The power transmitted through the waveguide is given by Pt is equal to Ztm by 2 integration ht ka square ds. And what does this capital T represent? The transverse component of the magnetic field. So power transmitted, it can be calculated as Ztm by 2 lambda c by lambda ka whole square 1 upon eta square integration Ez ka square ds. that is equal to ZTM by 2 lambda c by lambda का whole square an square upon eta square integration 0 से 2 pi 0 से a jn square h rho cos square n phi rho d phi d phi. So ZTM by 2 lambda c by lambda का whole square an square eta square. Now integration 0 से 2 pi would give me pi. So remaining integration is 0 से a rho jn square rho h d rho. This is standard property of Bessel function. So a standard function need to be solved using standard property of the Bessel function. What does it say? Integration rho jn का square h rho d rho would be equal to rho square by 2 jn dash का square rho h plus 1 minus n square upon rho square h square jn का square rho h. Here according to the boundary condition jn rho h is supposed to be 0. So this term vanishes. So 0 से a rho jn का square rho h is equal to a square by 2 jn का square ah plus 1 minus n square upon a square jn का square ah, which would be equal to a square by 2 jn का square ah. This term is 0 according to the boundary condition. Now you need to use equation number 3 in equation number 2 so that we get the transmitted power. So PT would now be equal to ZTM by 2 lambda c by lambda का whole square an का square pi a square jn dash का square ah upon eta square by eta square into 2. This is equation number 4. Now if I need to calculate attenuation constant, it must be equal to the ratio of PL upon twice PT. We are calculating for the TM modes. So this would be equal to RS by 2 lambda c by lambda का whole square an square a pi jn dash का square ah upon eta square, and this would be equal to twice eta square into 2 upon 2 ZTM lambda c by lambda का whole square an का square pi a square jn dash का ah का whole square. तो आपको इस इक्वेशन में PL और PT को सब्स्टिट्यूट करके सिंप्लीफाई करना है. So Z alpha TM would be equal to RS upon A ZTM. Remaining quantities are supposed to cancel. So RS upon A eta and ZTM would be eta into under root 1 minus lambda by lambda c ka whole square. So we get attenuation constant for TM modes in a circular waveguide. Now we look for attenuation constant for TEMN modes. The TEMN modes for circular waveguide are Hz is equal to Cn Jn h rho cos n phi e power minus gamma z. H rho would be equal to minus gamma upon h Cn Jn dash rho h cos n phi e power minus gamma z. H phi is equal to gamma upon rho h square Cn into n Jn rho h sin n phi e power minus gamma z. These modes have already been calculated by us in the earlier videos. So using directly the modes from those videos. E phi would be j omega mu upon rho h square Cn into n j n h rho sin n phi e power minus gamma z. E phi will be given by j omega mu upon h Cn jn dash h rho cos n phi e power minus gamma z. Now we need to calculate power lost per unit length of the guide, and that would be given by Rs by 2 integration over the entire surface ht ka square, once again the tangential component. Rs upon 2 would be equal to integration 0 to 2 pi h phi plus hz ka whole square at rho is equal to a d phi dz. Now just substitute the value of h phi and hz. So Rs by 2 integration 0 से 2 pi beta square Cn square n square upon rho square h power 4 Jn का square h rho sin square n phi plus Cn का square Jn का square rho h plus cos square n phi a d phi at rho is equal to a. Here dz is 1. Now just simplify. Rs by 2 is here, Cn का square Jn square h rho pi a, क्योंकि this integration would be half, that is a by 2 pi upon 2, that is pi here, and this integration would also be here. So beta square n square upon a square h power 4 plus 1, This gives me power lost in the form of equation number 1. After power lost, we need to calculate the power transmitted, and power transmitted through the equation here PT is equal to one upon 2 ZE eta square lambda c by lambda का whole square hz का square ds. PT would be equal to 1 upon twice ZE eta square lambda c by lambda का whole square 0 to a 0 to 2 pi Cn का square Jn square h rho cos square n phi d rho rho d phi. Now PT would be equal to eta square lambda c by lambda का whole square Cn का square pi upon 2 ZTE integration 0 से rho Jn square h rho d phi. Again, this has a standard answer, and that standard answer is given here: a square into jn square ha plus 1 minus n square upon ha ka square jn square ha. From the boundary condition, jn dash ha is equal to 0. So this equation simplifies. This term would be automatically 0. Power transmitted would be eta ka square lambda c by lambda ka square cn ka square pi a square jn square h rho 1 minus n square upon ha ka square, and that is now equation number 2. To calculate the power lost, the attenuation constant, we need to use the equation alpha would be equal to PL upon twice PT. Substitute the value of PL and PT from equation number 1 and 2 respectively. So this would be RS Cn ka square Jn ka square Ha pi a beta square n square upon a square h power 4 plus 1 upon 2 into 2 eta square lambda c by lambda ka square Cn square pi a square Jn square Ha upon 4 ZTE 1 minus n square upon Ha ka square. Just on simplification, I will get Rs is equal to beta square n square upon a square plus a square h power 4 plus 1 ZTE eta square lambda c by lambda ka whole square a square 1 minus n square upon Ha ka square. Now we have to use ZTE as eta upon under root of 1 minus lambda by lambda c ka square, and beta can be used as omega square mu epsilon minus h square. So alpha t would be equal to Rs omega square mu epsilon minus h square n square upon a square h power 4 plus 1 eta a upon under root of 1 minus lambda by lambda c ka whole square eta square lambda c by lambda ka whole square a square into 1 minus n square upon a square h square. Just simplify. It gives me Rs upon eta a lambda c by lambda ka whole square under root of 1 minus lambda by lambda c ka whole square omega square mu epsilon n square minus h square n square plus a square h power 4 upon a square h power 4 h square h square a square h square minus n square. Just simplify. On simplification, what we obtain is Rs upon a eta under root of 1 minus lambda by lambda c ka whole square omega square mu epsilon n square upon omega c mu square mu epsilon minus n square plus a square h square 1 upon a square h square minus n square 1 upon lambda c by lambda ka whole square. On simplification, I obtain Rs upon a eta. The first term remains the same. This would become lambda c by lambda ka whole square n square plus a square h square minus n square. So simplifying, I obtain Rs upon a eta under root of 1 minus lambda by lambda c ka whole square lambda by lambda c ka whole square upon n square upon ha ka square minus n square. This gives me attenuation constant for TM modes. So alpha TE would be equal to RS upon A eta under root 1 minus lambda by lambda c का whole square, lambda by lambda c का whole square plus upon n square p dash nm का square minus n square. P dash nm is the mth root of Bessel function Jn h rho is equal to 0. By observing the equations for alpha TE and alpha Tm, what do we find? That conduction attenuation depends on frequency, diameter A of the waveguide. The figure shows attenuation offered by a copper waveguide of radius 5 cm. The TE01 mode has minimum attenuation, though it is not a dominant mode. So we have TE01 which has minimum attenuation, though it is not the dominant mode. This figure shows the conduction attenuation as a function of frequency in gigahertz. Now alpha TE0M would be RS upon A eta Fc upon F ka square under root of 1 minus Fc by F ka square is equal to RS lambda by lambda c ka whole square A eta under root of 1 minus lambda by lambda c ka whole square. Now what are the utilities? Let us see the first one. RS increases as root F. So attenuation constant for TE0M modes in circular waveguide falls as F power minus 3 by 2. The rapid fall of attenuation constant is a unique feature of circular waveguide. What does it make its use into? This helps us to design very long low loss waveguide communication links. This rapid fall of attenuation constant gives a unique feature of circular waveguide which is made into designing very long low loss waveguide communication links. TE01 mode of circular waveguide has wall currents in the circumferential direction only. This property is used to design mode suppressors. A waveguide with high conductivity in circumferential direction and low conductivity in axial direction serves as mode suppressor. Use number 3. The TM01 mode has a radial field independent of the azimuthal angle phi. That is, it is same at a given radius. This property would help in design of rotary joints. This figure shows conductor attenuation for low loss TE0M modes in circular waveguide as a function of a frequency. See the fast rapid decrease with respect to frequency. Now we like to pick up quality factor Q of a waveguide. The quality vector for walls is written as QW is the omega times energy stored per unit length upon energy lost per unit length per second. In waveguides, the energy propagates at a group velocity Vg. So energy transmitted per second would be equal to Vg into energy stored per unit length. So energy stored per unit length would be equal to power transmitted upon Vg, that is power transmitted upon Vg. So QW would be equal to omega power transmitted upon Vg into power lost per unit length, that is omega Pt Vg PL. Since alpha is equal to PL upon twice Pt, so Pt upon PL would be 1 upon 2 alpha. So QW can be written as omega upon 2 alpha Vg. Omega upon 2 alpha and Vg can be written as Vp into under root of 1 minus lambda by lambda c ka whole square. Vp is nothing but the phase velocity. Alpha is attenuation per unit length. The waveguides are characterized by low value of alpha. So waveguides have very high Q values. Such sections of waveguide are used in microwave resonators and filters. The waveguides are characterized by low value of alpha. So they have very high values of Q. तो हम ऐसे सेक्शन ऑफ वेवगाइड्स को माइक्रोवेव रेजोनेटर और फिल्टर बनाने के काम में लेते हैं. QW को हम इस तरह भी लिख सकते हैं. QW can be written as omega upon Vg upon 2 alpha, and omega upon Vg is propagation phase constant beta. To find losses in the dielectric, we use the concept of complex frequency. omega is equal to omega 1 plus j omega 2 and define QD for dielectric loss. QD is defined as the ratio of imaginary component of frequency to the real component. So QD would be equal to the ratio omega 2 upon omega 1. The propagation constant gamma for a wave must be imaginary. So gamma can be written as under root of h square minus omega 1 minus omega 1 ka square minus omega 2 ka square mu epsilon minus sigma omega 2 mu plus j omega 1 mu sigma minus 2 omega 2 epsilon. For gamma to be imaginary, the first bracket must be negative and the second must vanish. तो ओमेगा 2 का वैल्यू आपके पास आ जाएगा सिग्मा अपॉन 2 एप्सिलॉन एंड ऑल्सो ओमेगा स्क्वायर वुड बी ओमेगा 1 का स्क्वायर प्लस ओमेगा 2 का स्क्वायर. सो क्यू डी कितना आ जाएगा ओमेगा 2 बाई ओमेगा 1 अंडर रूट ऑफ ओमेगा 1 बाई 2 ओमेगा 2 का होल स्क्वायर प्लस 1 बाई 4 एंड दैट वुड बी एप्सिलॉन ओमेगा 1 अपॉन सिग्मा. Thus, the QD is equal to ratio of dielectric current to the conduction current in a waveguide. The total Q value is written as 1 upon QT, that is the total value of the quality factor, is 1 upon QW due to the walls plus 1 upon Q due to dielectric. So students, this video completes our complete discussion on attenuation. Hope these videos have made your understanding of attenuation better. अगर आपको हमारे वीडियोस अच्छे लगते हैं तो आप उन्हें लाइक करें, कमेंट करें और चैनल को सब्सक्राइब करें, बेल आइकन बटन को प्रेस करें ताकि आने वाले नए वीडियोस का नोटिफिकेशन आपको समय पर मिल सके. थैंक्स एंड थैंक यू वेरी मच.